All right, so let me start off by showing you a graph that we've seen before. All right, here's a graph. What this shows you is, it shows you nuclear stability. Okay, this is the neutron numbers in a nucleus. This is the proton numbers in a nucleus. Okay, and what that black line tells you is if a nucleus has that many neutrons and protons, so for instance, these guys, all these guys have 30 neutrons and between 24 and 26 protons. All those black dots are stable nuclei. They won't decay radioactively. Okay, so they're stable nuclei. All these guys are unstable nuclei. All right, so what that means is these nuclei will decay radioactively and they will move towards stability. Okay, so that's why if a nucleus is unstable, it will radioactively decay so it becomes stable. Okay. What about these guys? So an 80 proton and a 90 neutron. What about this guy? The white stuff. Okay. What this white area is you can't make those nuclei. Okay. So you can't make a nuclei with 80 protons and 90 neutrons. Okay. So these are the only nuclei that we can make. The ones on the dark they're stable, and in the light blue are unstable nuclei. So we'll talk about these nuclei. Okay. And a nuclei can decay one of three ways. And when it decays, it's going towards stability is what it's trying to do. Okay, so here we go. So here's three ways a nuclei can decay. Okay, so it can alpha decay. So here's a parent nucleus, and it can emit an alpha particle. An alpha particle is just a helium nucleus. You see the guy on the right, top right, that's the helium atom. It has 2 protons and 2 neutrons, so it can decay via alpha decay. Okay, and then there's the daughter nucleus. Okay, so there's one way of decaying. The second way of decaying is beta decay, and in a beta decay, what is happening is one or two things are happening. Either a neutron is turning into a proton. Okay, what is the charge on the neutron? Neutral. It's a zero charge. The proton is a positively charged particle. Okay, so it's got to emit an electron as well, and then it emits a neutrino, something called a neutrino.
Can you spell that?
The neutrino, this is a yeah. Or a proton in a beta decay, a proton is turning into a neutron. Well, the proton is positively charged particle. Neutron is a neutral particle, plus something called a positron, plus an antineutrino. Okay, or this could be switch. I got to look it up. Okay, but it doesn't matter. So in a beta decay, a proton is being converted to a neutron, or a neutron is being converted to a proton. Okay, depending on what's happening. And when one of these decays happens, the daughter nucleus is in an excited state, and it emits a gamma photon and just becomes de-excited. Okay, so the nature of that is not changing. So those are one of three ways it can decay. Okay. All right, so now let me show you this to you in the diagram again. Okay, so let's go back here to the diagram, nuclear stability diagram. So let's say here's a nucleus that is unstable, and let's say it decays via alpha decay. Alpha decay meaning it emits an alpha particle that has 2 protons and 2 neutrons. Okay? So when it emits an alpha particle, 2 of its protons reduced and 2 neutrons reduced. So if a nucleus is here, 2 protons reducing makes it go 2 units to the left, and 2 neutrons emitted makes it go 2 units down. Okay? So it tries to get towards stability. So an unstable nucleus is trying to, this unstable nucleus is trying to get to stability. Okay, so essentially it moves diagonally down when it emits alpha particle. Okay? When it's doing a beta decay, so beta decay, when a proton is turning into a neutron plus a positron plus a neutrino, what is happening is this guy, it's reducing 1 proton and increasing 1 neutron. So nucleus here is moving like that towards stability. Okay. If it's a neutron turning into a proton in a beta decay, these are what's happening. If a neutron is turning into a proton, a nucleus from here, the neutron number is decreasing and proton number is increasing, so it's going like that. Okay?
Will it stop decaying once it reaches?
Yeah, once it reaches the line of stability, it'll stop decaying. So what happens if you're very far away from the line of stability?
It'll start to.
You might have multiple decays. Okay? So uranium, for instance, uranium-238, we'll learn about this, undergoes 6 decays. So there are 6 generations of daughters that are formed. Okay? Anyway, whenever you're unstable, you move toward stability. Okay? Did you guys understand that?
Last week when you were talking about carbon-14.
We'll talk about it today.
Okay.
All right? I'll fill in. We'll talk about a couple of clocks. Very interesting. Okay? All right, so everybody understand why a nucleus decays? Okay. So for instance, in a nuclear reactor, when you split the uranium nucleus, the daughter nuclei are radioactive there because they're very unstable. And one of the problems is they will radioactively decay some of the products will undergo decay for 25, 30,000 years, 100,000 years. So they'll be warm they'll be radioactive for that long. Okay? And even the Fukushima reactor, even once it was shut down, the products, okay? So, the tour on the nuclear reactor was very good. Okay, so again, an unstable nucleus tries to go towards stability. One of the decays is an alpha particle. The second mode of decay is a beta decay, which is a proton turning into a neutron or a neutron turning into a proton. And this is either an electron or an anti-electron, and here is the daughter nucleus. In these 2 decays, generally this daughter nucleus is in an excited state, and that excited daughter nucleus will emit a gamma photon and become de-excited. All right. All right, so let's say there's an unstable nucleus, and you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So let's say you have 10 of these guys. These are unstable nucleus. Which one is going to decay? It's a random process. You don't know which one is going to decay. Okay? So we define something called a half-life of the nucleus. Okay? And the half-life means after that, so if the half-life is 5 seconds, after 5 seconds, half of them will have decayed. And that's what that means. Okay? After another 5 seconds, the remaining half will decay. Okay, so that's how the decay process goes. you can't predict which nucleus will decay. Okay, so unstable nuclei decay according to the exponential decay law. So if you started with this many, that many, as time proceeds, the number that remain decay exponentially. Okay, so that's what the graph is telling you. You know? Half-life is the time required for 1/2 of the atomic nuclei of the radioactive sample to decay. Okay, so you saw in this table, see, in this table for these nuclides, for this half-life is 8.8 minutes for calcium 49. Calcium 49 is unstable. Okay, it decays radioactively and it decays via beta minus decay. So what is happening there? How does beta minus happen? A neutron in the nucleus is turning into a proton plus an electron plus a neutrino. That's what's happening. Okay, so this tells you that. So if a proton turns into a neutron, if a neutron turns into a proton, it has one more, so this calcium 49 becomes, see, where is calcium? Look at calcium is on the 4th row, the second one. Everybody see that?
Mm-hmm.
That's calcium. So when after beta decay, what does it become?
Neon.
Potassium?
Huh?
Potassium?
No, see, so one, in the beta decay, what happened? A neutron turned into a proton.
Oh, okay.
So 21, SC, whatever that is. Okay?
No.
No, it's not silicon.
Scandium.
Yeah, scandium. Okay? Very good, my friend. So it became scandium. Okay? All right, and the half-life is 8.8 minutes. Okay? Okay, so let's make sure we understand half-life. Let's say you have 1,000 atoms at T times calcium atom at T equal to 0. After 8.8 minutes, I'll write 8.8 minutes, you have 500 calcium 49. After 17.6 minutes, how many do you have? 250. After 26.4 minutes, you have 125 and so on. Did you guys understand that? All right. All right. So so when you observe alpha decay, it's mostly large nuclei that will emit alpha particles. Okay? So this is large unstable nucleus. It will emit a alpha particle, which is a helium nucleus. Okay? And there is the daughter nucleus. Okay? Generally, these daughter nuclei are also unstable and it will further decay. Okay? And the daughter nuclei's atomic number is, it has 2 less protons and 2 less neutrons. Okay. So uranium, okay, so let's say uranium 238 decays via alpha. So here's uranium 238, here's the alpha particle, and here is thorium 234. Okay? So it has 2 less protons and 4 less nucleons. With a half-life for 4.5 billion years. Okay? So this is the kind of stuff that is used to tell the age of the Earth. We know the Earth is 4.5 billion years old, and this is how we know. Okay? So you use this atomic clock. And I'll show you a little more details in a second. Okay? Did you guys understand that? All right. In a beta decay, either a neutron is turning into a proton or a proton is turning into a neutron. Okay? Electron, anti-neutrino. So there is this has it. An electron is goes with an anti-neutrino, and a positron goes with a neutrino. Okay? So proton, neutron. You guys know about antiparticles? This is an electron, and the positron is an antiparticle of an electron. Antiparticles destroy each other if they meet, okay? And neutrino. All right, so here's in carbon-14, here's what's happening. Carbon-14 is radioactive. It's unstable, okay? It has too many neutrons. It has 6 protons and 8 neutrons. And when you're light, what you want is, if you want to be stable, you want to have equal number of protons and neutrons, okay? So this has too many neutrons. And so one of the neutron gets turned into a proton. This is the decay happens, and an electron. And so now it'll have 7 protons, so it's become nitrogen. Okay, so radioactive decay is the only way you can have transmutation, where one element turns into another element. You remember in the old days, people used to try to make gold out of other elements. I guess. All right, so in this, what is happening is it has too many neutrons, so one neutron turns into a proton. This becomes nitrogen. There's the anti-neutrino and the electron. Okay. The half-life of this guy, this process, the half-life of this guy is about 6,000 years. Okay. Here's another carbon-10. What is the problem here? Carbon-10 has, very good. So how do you fix that?
The protons would break.
Turn a proton into a neutron. That's what happens. Okay, there's a solution to every problem. Okay? So turn a proton into a neutron, and so this turns into boron. See, there's carbon on the second row on the right, carbon 6. When you turn one proton into a neutron, you have one less proton, and it becomes C6 becomes B5. Okay? Okay. And so it becomes stable. Okay. So beta particles are either electrons or positrons. Okay. When okay, so gamma decay. What is gamma decay? So generally, so when this nucleus decays into a daughter nucleus, this daughter nucleus generally is in an excited state. And so it will emit a photon and gets de-excited, and that's a gamma decay. Okay? A nucleus in an excited state can decay to a lower energy level by emitting a photon. Okay? Gamma rays. So in a nuclear reactor, when you shoot a neutron at a uranium nucleus, it breaks up into 2 pieces, and these guys are generally in excited states, and they're also radioactive. I mean, they can emit alpha particle, beta particles, or gamma particles. Okay, so you get all kinds of radioactivity. So in an alpha and beta decay processes, the progeny nucleus, the daughter nucleus, is often left in an excited state and subsequently de-excites by gamma decay. Okay, in the medical industry, they use radium samples and stuff like that. So initially, if you start off with a radium sample, pretty soon that will have other elements that are decaying other processes, and that radium sample will emit all kinds of radiation. Okay, so radium will alpha decay and give you radon. Okay, and this radon will again alpha decay and give you polonium. This polonium will beta decay and give you astatine. And then one of these guys is in an excited state and will emit gamma radiation. So all the above decays are generally followed by gamma decay. So you started off with this sample, you get alpha particles coming out, beta particles coming out, and gamma rays coming out from that sample. Okay? All right. Okay, so here is the periodic table. Okay, it's a Sergei plot. And what it shows, well, it's not, the circuit plot shows you the following. So here's americium. It has 241 nucleons. It alpha decays, so 4 nucleons decrease. So it decreases by 2 protons and 2 neutrons. So here's how you show it on the diagram, okay? So this is the number of protons and this is the number of neutrons. Okay, this is that plot. This is that plot blown up. Okay, this is the line of stability, this plot in a big diagram. Okay. The circuit plot. Okay. So when you lose 2 protons, you went left and then you lost 2 neutrons. Okay, so when you alpha decay this nucleus, you go down diagonally 2 units. There is the daughter nucleus. That's the result. Okay, and so because the line of stability was going that way, then you're moving towards the line of stability. Okay. In a beta decay here, when you emit an electron, a neutron turned into a proton. So a neutron turned into a proton, your number of neutron decreased and 1 proton increased. So you're going from here to there. Okay. So this kind of decay happens when you're above the line of stability and you're moving towards the line of stability. Okay. This happens, this is a proton turning, when you emit a positive particle, it's a proton turning into a neutron inside the nucleus, and a proton decreases and a neutron increases. So this happens when you're going like that. Okay. So in this plot, okay, so you're emitting an electron. When you emit an electron, you're going like this. When you're emitting a proton, a positron, you're going like that. Okay, so this. Anyway, your ultimate goal is to land on the line of stability. Okay, so an alpha decay, you're going down like that. In a when an electron is emitted, you're going like that. When a positron is emitted, you're going like that. Okay, so that's what it's showing you. All right. All right, that's the Sergey plot. Okay, now we'll talk about nuclear reactions. Okay, so here's a target nucleus and you hit it with a neutron, for instance. Okay, and then here are the products. Here's the daughter nucleus and here's the alpha particle, for instance. So the notation is this is the projectile, there is the target, there's the daughter nucleus, and there's the side product. Okay, the notation is you're hitting this target with that guy, and that's the particle emitted, and there's the daughter nucleus. Okay. So here is the carbon-14 reaction. Okay, so you're getting neutrons from cosmic sources. Okay. These neutrons, so there's a steady stream of these neutrons coming. Okay, and the neutrons hit nitrogen. There's plenty of nitrogen in the atmosphere. 78% of the atmosphere is nitrogen. These neutrons hit nitrogen and knock off a proton. Okay, so when nitrogen loses a proton, see nitrogen 7, when it loses a proton, it becomes carbon. Okay. This was nitrogen 14, it got a neutron and lost a proton, it became carbon 14. What's the problem with carbon 14?
Unstable.
Why is it unstable?
Too many neutrons?
Huh?
Too many neutrons?
Too many neutrons. It's got 6 protons and 8 neutrons. So it's unstable and it will radioactively decay. Okay, so this is steadily happening. The rate of production is equal to the rate of decay. That's crucial. Okay, and it turns out that every billionth atom is a carbon-14. So for every billion carbon-12 atoms, 1 is carbon-14. Okay, so there's a steady state of that. For every billion carbon-12, there's 1 carbon-14. So here's a tree that is alive, And so every billionth atom in this is carbon-14, while it's taking in carbon dioxide and stuff like that. As long as it's alive, every billionth atom is carbon-14. Now, once the tree dies, now it can't incorporate carbon-14 anymore. And what happens to the carbon-14? It starts decaying, okay? So, let's say this tree died today, and it has 1,000 carbon-14 atoms. That can easily be calculated, okay? So, it has 1,000 carbon-14 atoms at time 0. 6,000 years from now, how many will it have? 500. 500. 12,000 years after it dies? 250. 18,000 years? 125. Easy. It died 18,000 years ago. So that's carbon dating. Yep. You can use this technique to date objects that are 50 to 100,000 years old. Okay?
So even though it's changing into different elements, it's still the same?
No, all you do is, so here's this dead piece of wood. All you do is you measure, so you measure the total number of carbon atoms, and then you measure how much carbon-14 is remaining. Okay. So let's say if it had 1 million carbon atoms, or it had 1 billion carbon atoms, for every billion there was only, you started with 1 carbon-14. So, okay. Everybody understand this? All right, so this is that. What if I want to date something that is 2 billion years old? This is no good. What do you do?
You did something with a longer.
Half-life, that's it. It's that simple. Did you guys understand that? All right, so let's look at another clock. Okay. All right, so carbon-14 half-life is 5,730 years and used for carbon dating objects. Okay. So here's uranium-lead dating. Okay. So let's say you have a volcano that spews out lava. Okay. And so if there is uranium in there, it will form a rock. Okay. The method is used to apply to zircon. This rock incorporates uranium and thorium atoms. Okay, the crystal structure of this, if there is lead in this rock, in this lava, lead won't get in here. So this rock will only have uranium and thorium atoms. Oh man. It does this. I got to get me a new iPad. Now the recording all got messed up. Oh, that's such a shame. All right, so this rock forms, it has uranium and thorium. Okay. Is it still messing up? Okay. But it doesn't have any lead when forming. As a result, newly formed zircon deposits will contain no lead. So if this was spewed out, formed from lava, okay? Hence, any lead found in the mineral is radiogenic, okay? So uranium decays to lead via a series of alpha and beta decays. Uranium-238 undergoes a total of 8 alpha and 6 beta decays. So uranium-238 will undergo 14 decays before it turns into lead. Uranium-235, so this will have uranium-238 and 235. Uranium-235 with daughters experience 7 alpha and 4 beta decays, so 11 decays before it turns into another form of lead. All right, so let's say this rock formed out of lava that was spewed out. Okay, it had no lead, and now several years later, in this rock, you have so same rock later, and these blue atoms are lead. Now you're going to count the lead atoms in here. Okay, and you're going to count the uranium atoms. And here's the graph. So you count. So uranium-238 decays into lead-206. Uranium-235 decays into lead-207. As more time goes on, more of lead is in the rock, right? Yeah. And as more time goes on, more of lead is there, okay? And so you measure this ratio and this ratio, okay? And what it's telling is if there's 15 atoms, lead-207 for every 235 atoms, there will be that many lead-206 to that many. The rock is 2.8 billion years old. Okay. If there's that many 207 to 235, the rock is 3 billion years old.
How do you know it was uranium before it was lead? Is it because you can only get
Oh, no.
lead-237 from?
Yeah. Oh, yes. So all those decay paths you've done in lab, you can only go from here to there and stuff like that.
Okay.
So if you're here, you know where you started from. So there we go. That's 3 billion years old. Okay. So you, depending on what age you're trying to measure, you use different clocks. Okay. So here's a neutron gamma reaction. What that means is you're shooting a target with a neutron and it's spitting out a gamma particle. So you shoot a neutron at U-238, it absorbs the neutron, becomes U-239, it's in an excited state, and it emits a gamma, which is a photon. Okay? So this happens in a nuclear reactor. In a nuclear reactor, fuel is enriched. Okay, what that means is if you go mine uranium naturally, it's 238 is 99.2%, and uranium-235 is 0.8%, something like that. Okay, and to make it into a useful fuel, you have to enrich it. You got to increase the percentage of that. Okay, so you saw that in the nuclear reactor at UF. Okay, commercial reactors do 5%, but at UF it was 80% U-238 and 20%, less than 20% U-235. Okay, so that's what enrichment means. Okay. All right, so there's plenty of U-238, and those neutrons hitting U-238 turn it into U-239, and it emits a gamma particle. An important example of the above reaction for nuclear reactors is the neutron capture of U-238 followed by a gamma emission. All right, So reactions are classified as exothermic and endothermic. Okay. Exothermic reactions are, here are the ingredients and here are the products. The energy of the product is less, so it will emit energy. It'll give out energy. So an exothermic reaction gives out energy. So for instance, when you burn wood carbon is combining with oxygen, and the products have less energy, and when you burn wood, you get energy. When you exothermic reaction is endothermic reaction is you have to put in energy and the product have higher energy. Okay, so when you go from what are the energy molecules in your body? ATP. So ATP has higher energy, and you're making ADP. ATP is triphosphate, adenosine triphosphate. This is diphosphate. So you're storing energy. That's an endothermic reaction. So this is your battery, and then you use the energy stored in here in your body all the time. Okay, so your body, at any given time, you have only 2 to 3 grams of ATP in your body, or something like that. But you're making, so you're using energy, it goes there, and then you constantly use the energy from the food you're using to make these guys. You're making your body's weight worth of ATP every day. Okay, so that's a battery. Yeah. All right, here's why we like nuclear energy. Here's why nuclear energy is good. Okay, so if you could get energy out of 1 kg of 235, uranium-235, 1 kg is that much. Hold your bottle up. That's 1 kg. Okay. The energy out of 1 kg of uranium-235 would be the same as the energy of 3 million kg of coal. And then what is the other big benefit? No CO2. That's the mantra. You want an energy source that doesn't increase greenhouse gases in the atmosphere. What other source won't increase greenhouse gases? What other energy source?
Like
Wind and solar.
Mhm.
Yeah. And then there's geothermal and wave, but those are small players. So if you come back 300 years from now, if you come back to Earth 300 years from now, the 3 energy sources will be
Wind
wind, solar,
and nuclear.
Yeah. Hopefully not even in 300 years. Hopefully, for your sake, within 100 years, okay? So if you burn 1 carbon atom, and we'll see the numbers later, you get about 4 eV of energy. You split 1 uranium nucleus, you get 200 MeV of energy. For 1 carbon atom and 1 uranium atom, you get 50 million times more energy. Okay? I think I'll take 50 million any day. We have about 100 nuclear power plants operating, and there are the nuclear power plants. Each nuclear power plant is 1 gigawatt. A gigawatt is like a Hoover Dam. You can run roughly 1 million homes, less than that. Okay. 2/3 of the reactors are pressurized water reactors. Okay. So the water under pressure is removing heat from the reaction. We'll talk about this in the next chapter. We'll talk about reactors. 1/3 are boiling water reactors. So nuclear reactors produce 20% of our electricity. Yeah. So we have flatlined, we haven't been making reactors. But hopefully that'll change. With AI and all that, all private companies are starting to commission their own reactors. Greenpeace admits that they made a mistake fighting against nuclear reactors. But anyway, China is going forward with nuclear reactors. So China has become largely self-sufficient in reactor design and construction, as well as other aspects of fuel cycles. Okay. China's policy to go global with exporting nuclear technology. Okay, China's policy is closed fuel cycle. What does that mean, you think?
They're just gonna cycle.
So remember, even a spent fuel rod has only 50% of the uranium-235 is used. So they'll reprocess that and then use that. France does that. Okay.
Is it just less efficient?
It's an expensive process, but it's like the more you use the process, the cheaper it gets. France has been doing that. We used to do that, but we should start doing it again. Yeah. There are 440 nuclear reactors in the world, and see, each is producing. This means gigawatt electricity. Gigawatt means 1 billion watts. Soon as you see gigawatts, think of a Hoover Dam. So that's one Hoover Dam. This is that much electricity. Okay, to produce 1 gigawatt of electricity, what you need is 3 gigawatts of heat. Okay, only 1/3 of the heat is converted to electricity. So you'll see those numbers. See, France gets 75% of its electricity from nuclear power. We get 20% of our electricity from nuclear power. Okay. So there's 436 in operation, 16 construction, and 200 have been shut down. 10% of the world's electricity is generated by nuclear reactors. Okay. So what needs to happen? Right now, solar and wind are the cheapest. Nuclear is a little expensive. It's gotten a bad rap, and we're just trying to make it bulletproof, beyond bulletproof. You got to be reasonable. You got to come up with safer designs, things that shut off automatically and all that, and there are these designs. So there are safer ways to make it anyway. And one of the big things was nuclear non-proliferation, but you got to be reasonable about that as well. But nuclear power is great. Do you guys know what? Okay, let me show you another guy. All right. Capacity factor. What do you think that means? So this is one of the more important facts. Okay, so what is a gigawatt? Huh? Very good. You see, she's listening. It's a large power plant. So if you try to build a Hoover Dam with solar power, and I'm just giving you rough numbers, it costs $3 to $5 billion. Okay, depending on the land and stuff like that. Wind is also roughly that. Nuclear power plant, probably, on the other hand, costs can overrun. You can't give an estimate. Let's say $20 billion, just because I don't know, you're trying to, maybe more. You can't build a Hoover Dam today, it probably costs $30 billion, so who knows? Okay. Here's the point. You invest this much money, what do you want the money to do?
Making money?
Make your money. You want it to be earning your money. Okay, so a solar power plant. Solar is still cheapest, I'm just telling you. I'm just trying to explain capacity factor to you. What capacity factor tells you is solar, it can't work half the time because half the time it's night. And then the sunlight is not equally intense all during the day. So your $3 billion is working 25% of the time, essentially, on the average. Look at this, a nuclear power plant is working 100% of the time. A nuclear power plant is working all the time. Natural gas is expensive, but you need natural gas plants to turn on when the demand is peak, okay? And it's easy to turn on, but natural gas is expensive. Okay. Hydropower, why is the capacity factor low? Because you depend on rains to fill the dam. Okay. All right, so here's an important thing you want to understand. Okay, so if you look at, let's say, a city's electricity demands, okay, as demand versus time. Okay, this could be time of the day. Okay, this would be around noon and so on. So you have peak use during noon. This is called baseline needs. You need that much no matter what time of the day. This is best solved by nuclear. Okay. So you just have to make nuclear power reasonably priced, and nuclear should be a big part of your energy equation. Okay? So we'll talk about fission reactors. That is, you're taking a heavy nucleus and splitting into two. We are also building fusion reactors. What is the advantage between fission and fusion? What is the advantage of fusion? Okay, so fission reaction is you're taking a uranium-238 nucleus and 235 nucleus plus energy. Fusion reaction is you're taking 4 protons and turning it into a helium nucleus. So this is how the sun makes energy. And in a fission reactor, you're splitting a uranium nucleus. Okay, you get energy. The thing is, with fusion, there's no radioactive byproducts. So these guys are radioactive for 25,000 to 100,000 years. Okay. And well, it's not that big of a deal, but, and this technology we've mastered, this is just coming online. So maybe 300 years from now, it'll be this wind and solar. Okay. All right, guys.